the point Zeros and Singularities of Analytic Functions by Dr. Goutam Kumar Ghosh. Definition: if alpha is a regular point of an analytic function f, if f alpha equal to 0, then alpha is called a 0 of f. Definition: the point z equal to alpha is called a 0 of f of order or multiplicity m if in some neighborhood of alpha f can be expressed in a Taylor series of the form fz is equal to summation of n equal to m to infinity an z minus alpha to the power n, where am not equal to 0. Theorem: a point alpha is a 0 of f of multiplicity m if and only if in some neighborhood of alpha f can be expressed in the form f z is equal to z minus alpha whole to the power m into phi z, where phi is analytic and alpha at alpha and phi alpha not equal to 0. Theorem: if alpha is a 0 of an analytic function f, then there exists a neighborhood of alpha which contains no other 0 of f unless the function is identically 0. In other words, zeros of an analytic function are isolated points. A regular point and singular point: a point alpha is called a regular point or an ordinary point of a function f if f is analytic at alpha, otherwise alpha is called a singular point or a singularity of f. Isolated singularity: let f be an analytic function with a singular point at z equal to alpha if there exists a neighborhood of alpha which contains no other singular point of f, then alpha is called an isolated singular point or an isolated singularity of f. Suppose that alpha is an isolated singularity of the function f. In this case, f can be expanded in a Laura series fz is equal to n summation of n equal to 0 to infinity an z minus alpha to the power n plus summation of n equal to 1 to infinity bn z minus alpha to the power minus n in a domain 0 less than mod of z minus alpha less than r, where r is the distance of the point alpha from the nearest singularity of f other than alpha itself. Principal and regular part: the portion of the series involving negative power of z minus alpha, that is summation of n equal to 1 to infinity bn z minus alpha to the power minus n, is called the principal part of f at alpha, while the series of non-negative powers of z minus alpha, that is summation of n equal to 1 to infinity an z minus alpha to the power n, is called a regular part of f at alpha. A removable singularity: suppose that all the coefficients bn are 0, we then call z is equal to alpha are removable singularity of f, because we can make f regular in mod z minus alpha less than r by suitably defining its value at alpha. Example: fz is equal to sin z by z, z not equal to 0 when z equal to 0. Pole: suppose that the principal part of f at z is equal to alpha contains a finite number of terms only, then f is said to have a pole at z is equal to alpha if bm m greater than equal to 1 is the last non-vanishing coefficients in the principal part, then fz is equal to summation of n equal to 0 to infinity a n z minus alpha to the power n plus b1 by z minus alpha plus dot 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 plus bm by z minus alpha to the power m in 0 less than mod z minus alpha less than r, and the pole is said to be of multiplicity or order m. Example, fz is equal to z square minus 2z plus 3 by z minus 2 equal to 2 plus z minus 2 plus 3 by z minus 2. The function fz has a simple pole at z equal to 2. Essential singularity, the principal part of f at z equal to alpha contains infinitely many non-zero terms. The point z is equal to alpha is then called an essential singularity of f. In this case, fz is equal to n equal to 0 to infinity a n z minus alpha to the power n plus n equal to 1 to infinity summation of b n z minus alpha to the power minus n, where the last series does not terminate but converges for all z in mod z minus alpha greater than 0 less than r. Example, e to the power 1 by z 1 plus 1 by z plus equal to 1 plus 1 by z plus 1 by factorial to 1 by z square plus dot 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 has an essential singularity at z is equal to 0. Note, if a singularity is non-isolated, then also we call it an essential singularity. Thank you.